Good afternoon. So my name is Anderson Bravalheri. I am part of the team in Smart Internet Lab that works with orchestration. And most recently, we have been working with orchestration of Mac applications together with our partner, Samsung, here in UK. So when we talk about Mac applications, what we are usually referring to is a class of applications that have very high requirements, for example, ultra reliable, low latency communications, or that at least require a very high network bandwidth. And therefore, these applications and also the network itself can be optimized by moving the applications closer to the user and therefore alleviating the bandwidth and the traffic. The problem with this is that when we move the application closer to the user is constantly moving, right? So if the user moving away from the access point, we have to move the application together with the users. So if we take, for example, a game that's an application that requires a lot of bandwidth because we have to stream video. We are talking here about server rendered game. So we have light devices and a very strong server running the game completely on the remote server. We have a part of the application that receives the input from the user and process that input in a way that it creates an internal state. So that internal state then is used by a different part of the application to render the video and then stream back to the user. When the user moves away, there's a handover between an access point and the other access point. What we have to do is we have to create a new instance of that application, the new node, and also move the state. Then this application will be able to continue streaming. And we want to do all of that without the user knowing about it. So it's very difficult because the problem here is that creating a new instance of the application, migrating the state takes time. So what we have been proposing is the usage of orchestration and intelligent techniques to anticipate these handovers and start synchronizing the state before the handover actually takes place, right? So for that, what we are proposing here is to monitor the radio parameters, especially the strength, the power of the signal that's being received, the RSIP, and pipe this monitoring data into two mathematical models, computational models that can be used. The first one to predict what would be the future values for this RSIP, for the power of the signal that we are receiving, and the second one that receives as an input these predicted values to classify, to tell us exactly which is the most likely access point that the user is going to be closer to in the future. So in other words, we have a regression problem. So we have a time series data that we want to do some regression and be able to predict what would be the future values. And then based on these future values, we want to classify what is the closest access point that the user will be going towards you. These all based on the radio parameters. So one technique that we have been studied, the first one that we have studied is called gradient boosting. And gradient boosting is a way of using decision trees to perform, in this case, regression. So we have a series of trees. Each one of the each tree is trying to minimize the errors that the previous tree obtained in terms of predictions, right? The way we do that and why it's called gradient boosting is because we define a loss function that is going to, given the value of the data, the real value of the data that we observe and the predictions, it's going to try to fit for each leaf in this tree, for each tree, what would be the value that minimizes this loss, right? So we use the derivative function here, and therefore we call it gradient boosting. We use the derivative to calculate the values for each one of the leaves. In particular, we used XGBoost, that is a special gradient boosting technique that chooses very carefully this loss function in a way that you have very efficient, computationally efficient algorithm. So you can calculate those things very fast and precise. So you don't have to do any gradient descent. You have an analytical solution, and also the way you calculate the solution is very, very efficient. So that's what XGBoost is about. We also have studied a second technique using neural networks now. And for this, for the neural network that we are using in the predictor, we use some special structures that are called Lstm, so long short-term memory. They are especially recursive neural networks that are very much used for processing time series and sequential data. So they are very special. They are very famous for this application that we have used that. But adding to these structures, we have added some extra layers to do normalization that we are also training which is the best normalization because the strength of the signal might vary depending on the region where you are or depending on the antennas that you have available. So we are doing some normalization and therefore denormalization in the end. And we are piping this data into a multi-layer perceptron. It's just a fancy term for machine learning that is a series of linear transformations with interleaved with non-linear functions, non-linear activation function. This is a very famous one that we have been using. So that this is the structure of neural networks that we have been using for doing the prediction of RSRP. In terms of the classification task, the second task that we have, we are also using very similar constructs. So the same XGBoost technique. The difference here for the XGBoost that we chose is slightly different, is slightly more complicated loss function. And for the neural network, we can simplify the neural network. Instead of using the recursive LSM, we can use convolution. So we can use convolutional layers in this case. Something that's important to do when we are using neural networks is that we want the classifier to predict what's the most likely access point. Therefore, we need to have as an output probabilities, right? So the neural network have to output probabilities, which means that they have to these outputs have to respect probability characteristics. In other words, have to sum to 1. There's a trick to do that. That's using this softmax function that we are applying here as well. So we started. So after developing these models and studying them, we started doing some experiments in our testbed here in Bristol in the harbor side. So in the harbor side, we have a 5G testbed that's available, and we started going there and performing a series of different trajectories, measuring the RSRP data for the different antennas, for the different access points here, and also collecting the information to which access point the 5G device was connected at that point in time. So as you can see here in the traffic, in this graph. It's a bit challenging because each trace, in order to be relevant to our research, it has to be slightly long. So around 30 minutes at least, which means that in 2 hours of doing continuous experiment, you're going to end up with 4 traces, which is absolutely nothing to train your neural network or the XGBoost, any machine learning model. So we investigated other techniques to do that in a more efficient way. And one of the things that we came across was this concept of transfer learning. In transfer learning, you have 2 different tasks. Like you can create models for 2 different tasks. You have a task in the source model, that's how we call that's the source domain. That's a task that you have available data to create a model. So it's very easy to get the data and you can create this model fairly easy and simple way. But you are actually interested in creating a second task, a model to solve a second task for which you don't have that much data available or is more difficult, etc. So the idea in transfer learning is that you can reuse the model or reuse at least parts of the model from one task that you can train easily to another task that's more difficult to train. And there are different ways of doing it, depending if your tasks are similar, how similar are your tasks, or how similar are your domains. In our case, we wanted to simplify and be able to use a very easy way of doing transfer learning. So for us, we try to reach a domain that is very similar. So it's practically the same, and with tasks that are exactly the same. And that domain clearly came to us in the form of a simulation. So there are some models, mathematical models that are regularized by some entities like 3GPP, etc., that you can use to calculate or to estimate, to model how the RSRP values will change according to the area that you are. So we have implemented these models, these mathematical models in a simulation, and we have inputted these models with the same overall parameters that we have in our testbed, so the position of the antennas, the launching power, etc. And we created a series of random trajectories. And using this simulation, we were able to obtain lots of data in a much faster way. So in minutes, you can obtain hundreds of traces for the RSRP value. And using this data, we first trained the model. And since the input data is exactly the same and the domain is mostly the same, they are not exactly the same, because one is simulation, the other is real life, which changes a lot. But since they are very similar, what we did is we added a few extra training cycles to our model. There are other ways of implementing it using transfer learning. You can add other layers to the model, or you can add previous learning layers in order to adapt the input data. But what we did was the most simple basic thing, that is adding a few training cycles to it. And we were able to do the results were very positive in this way. So here I'm showing one of the results. Here linear is just a very basic comparison that doesn't really matter that much for us, because it's very imprecise. But what it is basically using the last measurements and try to do a linear regression, a linear extrapolation of the data. And here we have the mean average error, mean absolute error, and we can see that we cannot use this in real life because the errors are very high when we are using the linear extrapolation. But just for us to have an idea on how these models can work. So we have done experiments with both XGBoost and Lstm, and we can see that they are very good in terms of how good how they fit the data. Right? So we have experiments here for 3 different amounts of time. So 2 seconds, 8 seconds, 16 seconds. We could go further. Indeed, we were, but we can see that the quality of the prediction gets worse once we go there. So R2 here is just our coefficient of determination. It's just a regression metric, and we can see that it gets worse if we try to look too much into the future. In terms of the classifier here, we have this metric that's the F1 score. That's how good is your classification. 1 is the best. Sorry, in the previous slide, 1 is also the best thing that you can do in terms of R2. And here we can see that for both Lstm and XGBoost, they are close to 1. They are at least bigger than 9. Something that we notice is, in our experience, at least Lstm is slightly better than XGBoost, but they both work fine. We had some challenges when we were doing that, especially regarding the devices that we have available in the market. So it's very difficult to measure the RSRP with the frequency that we wanted. We wanted to sample it very regularly, at least less than half a second. And the devices that we could find difficult to do that sample, not because the device is not capable to do that, but the APIs that we have available for programming those devices to measure, they were not exposing these things. So we have to go with a specialized vendor and get these metrics in order from. There are alternative ways you can try to compensate this lack of sampling with adding extra data from the GPS, but we wanted to not go there, because with GPS you have some privacy concerns and etc. That at least with the radio parameters, it's less obvious how you can steal private data from the user. In terms of conclusions and future work, we have shown some models that have high accuracy levels for the handovers. We have also showed that we can use simulation to try to reduce the amount of data that's required to train it. And now the research that we are working right now is to use those things to promote these proactive actions for dynamic resource allocation. So we want to use this knowledge to be able to start synchronizing earlier the state and shutting down as soon as possible these instances of the application that you're not using. That's for energy cost reductions and also improving the perception of the delay that the user is having. Well, I think I ran out of the time, but thank you very much. That's my mail.
Yeah, thanks very much, Anderson. Yeah, we've got time for one question. So let me have a look in the questions there. So Ventaska Wilru asked, can we choose any other parameter as opposed to RSRP?
Yes, there are other parameters. We went for RSRP because it's the most obvious. So if you go to the documents in the through GPP, for example, you can see that the algorithms that decide how to hand over, when it's time to hand over, they are mostly based on the strength of the signer, the power of the signer that you are receiving. Of course, this will depend on the implementation of the vendors for the antennas and also for the UEs, but this is the more obvious ones. You have other parameters, as I mentioned in the application here. People tend to use a lot of GPS, but because of privacy concerns, we wanted to avoid using GPS. We have other. We can use other parameters also. There's another one. I forgot now the name. That there's a RSRQ. I think that's the other parameter that can enhance as well. But my view is that RSRP is fundamental. You can have more of those in terms of radio parameters, but I would say that RSRP is fundamental.
Okay, thank you very much. Okay, we'll move on to the next speaker now. Thank you again.
Thank you.